we'll first take a look at the polynomial functions. Now, polynomials can have all sorts of exponents. For example, these are called first-degree polynomials because the largest exponent is a 1. The graph of first-degree polynomials is always a straight line. We know that because these are one of the simpler kinds of functions that we've studied in the past. Degree 2, we've just got through studying, are called quadratics, exponent of 2. They're going to be parabolas. Now, degree 3, we haven't done much with in the past. Third degree means the highest exponent is a 3. You can have other exponents, but the largest one would be a 3. Notice that the graphs have a similar shape to them. We'll talk about the general idea of that shape in just a moment. Here's fourth degree polynomials, exponents of 4. The graphs likewise have similar shapes. We'll talk about those shapes and see if we can't get an idea about drawing graphs of such things. Fifth degree polynomials look a lot like the third degree polynomials. After studying a lot of these, we kind of break them down into two groups. The odd degree polynomials are the ones that have exponents like 3 and 5 and 7 and so on. And the odd degree polynomials, if they have a positive number on the highest degree term, that means in the first one on the front of the x, second one on the front of the x cubed, third one on the front of the x to the 5, then you notice that the direction is upper right and lower left. So it's always leading down to the left and up to the right. Now, if the negative number is on the highest degree term, it's just opposite of that. On all of these graphs, the left side is going up and the right side is going down. Even degree polynomials are slightly different. If it's positive, then they're going up on both sides. If it's negative, then the graph is going down on both sides. Now, polynomials are continuous, meaning one continuous line without any breaks in it for all values of x. Where it crosses the x-axis, we call that the x-intercepts or the roots or the zeros of the polynomial, and that's oftentimes what we're interested in finding for polynomials. The process for finding that algebraically is fairly involved. However, the problems we're going to be taking a look at involving polynomials are, first off, how do we use our calculator's regression feature to come up with a polynomial to fit some information. This problem is similar to what we see in the homework and on test. We want to find a polynomial that fits this data where the length is x and the weight is y. So we'll take out our calculator. In the stat edit, we will enter the table of values. Then we will calculate the cubic regression. That means a third degree polynomial that matches this data. Now from here we want to just verify that L1 and L2 is where we indeed did type our data, and then just push the calculate. And this is what we see. Now again, looking at the top line, it tells us we've got a third degree polynomial where the coefficient of the x cubed term is the a, that's listed just below it. The coefficient of x squared is the b, Coefficient of x is the c, and then the constant d is listed second from the bottom. The r squared has no significance for us. And so here's our polynomial model. Now, if we take that polynomial model, we should be able to answer questions concerning the model and the data. According to the model, what would a 20-inch fish weigh? Well, 20 inches is the x, so we want to substitute a 20 for the x. And type that into our calculator. Here are the other kind of functions that we want to take a look at in this section. Rational functions means fractions, where we have a polynomial on top and a polynomial on bottom. Here's the graph of a typical rational function, and you notice the red dotted lines that appear on the computer-generated graph are called asymptotes. We can find where the asymptotes are by considering the denominator of the rational function. The top of the rational function, the numerator, gives us the x-intercepts. So we can take the top, set it equal to 0, and solve for x by either factoring or using the quadratic formula to find our x-intercepts. The bottom is where we have asymptotes. If we take the x squared minus 4 and set it equal to 0, and again use either the factoring or the quadratic formula to solve for x, we see that that's where the asymptotes are. Horizontal asymptotes are where we see the graph leveling off. If you look at this computer-generated graph on the right side and the left side, it looks as if it levels off at about 1. Here's a little reminder of how we can go about determining whether it levels off or not and what it might level off to. To find the horizontal asymptotes, we consider the degrees. Either, first, on the left, the degrees are the same, in which case we divide the coefficients to find the horizontal asymptote. In this example, 3 divided by 1 would be 3. The second one, you notice that the degree of the top is smaller than the degree of the bottom. And so, if the degree of the top is smaller than the degree of the bottom, the horizontal asymptote will always be the x-axis, or y equals 0. If, however, the degree of the top is larger than the degree of the bottom, there are no horizontal asymptotes. Now, finally, we're going to take this function, which they say is a model for a cost and benefit of removing a pollution. X represents the amount of pollution. Y represents the cost. Notice it's in thousands of dollars. And so to determine the cost of removing 20% of the pollutants, notice that the 20% is the x. So we plug 20% for x. Do the calculation. Now 1.875, the y value, means 1.875 thousandths. That's 1,875. We do the same thing with 50%. Plug in a 50, do the calculation. Remember, that's 7.5 thousandths, or 7,500. Same thing with 90%. Notice how the costs are getting larger. Now, is it feasible to remove 100% of the pollutants? Can we plug a 100 in place of the x? Well, 100 minus 100 on the bottom would give 0. And for rational functions, one of the basic premises is you cannot have 0 on bottom. So no, it is not possible.